Consider the vibration of the two atoms in the HCl molecule shown in figure 1423. There is only a single vibrational mode where the hydrogen and chlorine atoms are alternatively closer and farther away from each other, a stretching mode. For simplicity, the arrows indicating the atom's direction of motion point in a single direction only. It is understood that in the course of a full vibration, the atoms move in opposite directions also. Note too that the lengths of the arrows are different. The hydrogen atom is shown moving farther than the chlorine atom. This preserves the position in the center of mass of the molecule, so it does not change. A single vibration agrees with 3n minus 5 expression for the number of vibrations in a molecule. For HCl, 3n minus 5 is 3 times 2 minus 5, which equals to 1. The two atoms in HCl can be brought as sort of a classical harmonic oscillator composed of two masses, the two atoms, connected by a spring, a chemical bond. This harmonic oscillator vibrates with a frequency of about 8.65 times 10 to the 13th hertz, or 86,500 gigahertz. Therefore, it absorbs the light that has the same frequency of 86,500 gigahertz. Light of this frequency has a wavelength about 3.46 micrometers, or 3.46 microns, which has an infrared region spectrum. In units of wave numbers, this light has a frequency of 2,886 centimeters to the negative first. Consider the possible vibrations of the three atoms in the H2O molecule. This molecule has 3 times 3 minus 6, which is equal to 3 vibrational degrees of freedom. What are they? One can imagine that the three atoms in water move about a complicated dance that might be difficult to understand. However, the vibrational spectrum of water shows 3 and only 3 distinct absorptions at 3,756, 3,657, and 1,595 reciprocal centimeters. This must correspond to the frequencies of the atoms in the three normal modes of water. The motions of the atoms in these normal modes, which can be determined mathematically, are illustrated in figure 1424. Notice that the vectors illustrated have different lengths so as to keep the center of mass in the same position. Again, only part of the motion is illustrated. The atoms also move in the reverse direction in the course of a single vibration. The normal vibrational modes of H2O are generally referred to in decreasing order of wave number: the asymmetric stretching mode, the symmetric stretching mode, and the bending mode. No matter how complicated the molecule, the motions of the atom with respect to each other can be treated solely as if the atoms were moving in normal modes. This allows us to only consider normal modes. More importantly, because of symmetry, so the normal modes of a large molecule are exactly the same as the others. Consider again the CH stretches of benzene, C6H6. Because of the six-fold symmetry of benzene, we might expect that they are described equivalently, and to a certain extent this is true. As such, these normal modes have the same vibrational frequency. The total number of unique normal modes therefore depends on two things: the number of atoms in the molecule, as indicated by the 3n minus 5 or 3n minus 6 number of normal modes, and the symmetry of the molecule. The higher the symmetry, the fewer the number of independent normal modes. Section 1410. Quantum mechanical treatment of vibrations. When one considers a diatomic molecule, it can be compared to a harmonic oscillator as defined by Hooke's law. F is equal to negative kx. Equation 1428. Where force F acting against a displacement x is proportional to x. We are ignoring the vector aspects of f and x here. The proportionality constant k is therefore called the force constant, and it has units of force per distance like newtons per meter or millidynes per angstrom. An ideal harmonic oscillator is also defined as having a potential energy of V is equal to the negative integral of f dx, which is equal to 1 half kx squared, equation 1429. The plot of a potential energy versus displacement is shown in figure 1425. In the first approximation, diatomic molecules can be considered in terms of quantum mechanical harmonic oscillators having a reduced mass mu, which, recall, is related to two masses of atoms m1 and m2. Mu is equal to m1 times m2 over m1 plus m2, or equivalently, 1 over mu is equal to 1 over m1 plus 1 over m2. Equation 1430. By making this ideal harmonic oscillator assumption, we make the wave functions and energies for the ideal harmonic oscillator directly applicable to the diatomic molecule's vibrations. In particular, since spectroscopy deals with the differences in energy states, we are particularly interested in the fact that the energy of vibration is equal to h nu times v plus 1 half, where v is equal to 0, 1, 2, 3, and so on. Equation 1431, where h is Planck's constant, nu is the classical frequency predicted by Hooke's law, and v is vibrational quantum numbers. Be careful not to confuse v with nu. That is, we expect that the vibrational energy of the diatomic molecule is quantized given by equation 1431 above. If the energies of the vibrational states are quantized, then the differences in the energies will have the same certain values. Diatomic molecules are particularly easy to treat quantum mechanically because they are described in terms of the classical harmonic oscillator. For example, the expression nu is equal to 1 over 2 pi times the square root of k over mu is equal to equation 1432. It relates the classical force constant and reduced mass of the oscillator to its frequency, and it's a valid mathematical tool. It is relatively easy to extend some concepts to other vibrational motions of larger molecules. The vibrations act as ideal harmonic oscillators that have certain wave function and certain quantized energies. However, normal modes are vibrations of all atoms in a molecule, not just two, so expressions like 1432 aren't directly applicable, even if the force constant for a polyatomic motion is used. On the other hand, many modes are largely motions of only a few connected atoms of a large molecule, so it is not uncommon to hear of CH stretches or CH2 bends, or such localized types of motion, even for large molecules. Technically, such labels are incorrect, but practically they are useful in qualitatively describing the normal mode of the molecule. It is not necessary to convert a wave number into a frequency value when doing an example like the one above, because the two quantities are directly proportional to each other. Also, even if a molecule isn't a diatomic molecule, and even though a normal mode consists of vibrations of all atoms in a molecule, in many cases, for stretching type motions, a diatomic approximation can be made for isotopic substitution. The next example illustrates that. Section 1411, Selection Rules for Vibrational Spectroscopy. As with rotational spectroscopy, there are several ways of stating selection rules for spectral transitions involving vibrational states of a molecule. There is a gross selection rule which generalizes the appearance of absorptions or emissions involving vibrational energy levels. There is also a more specific quantum number-based selection rule for allowed transitions. Finally, there is a selection rule that can be based on group theoretical concerns, which we are not considering for rotations. Recall that light is an electromagnetic field that's oscillating. It can interact with other electromagnetic fields, like the dipole moment of a molecule. This interaction dictated our gross selection rule for pure rotations. The molecule must have a permanent dipole in order to have a pure rotational spectrum. This is because the rotating dipole acts as an electromagnetic field that's oscillating, not changing in its magnitude, but direction. As a vector, the dipole moment can oscillate by changing either its magnitude, direction, or both in order to be detectable by another oscillating electromagnetic field, like the light. For vibrations, the key to interacting with light is based on the changing magnitude of the dipole moment of the molecule during its vibration. The dipole moment of a molecule is defined as the charge differential times the distance between the differential charges. The distance between charges changes as the atoms of the molecule vibrate. As it changes, an oscillating electric field is created. It can interact with the electromagnetic field of light. Suppose there is no dipole moment changing its magnitude due to changing distance. There may be fleeting, non-permanent dipoles present as a result of the symmetry-destroying distortions imposed on the molecule during vibrational motion. This will be enough to interact with light. If, however, there is not either a change in the dipole magnitude or directions, then there is no oscillating field to interact with, and the light uh, is neither absorbed nor emitted. The selection rule for vibrations is the presence of a dipole moment that changes during the course of vibration. A varying dipole moment is required. Note that this does not imply that the molecule must have a different dipole moment in order to have a vibrational spectrum. Consider the molecule methane, CH4. It has no permanent dipole moment, thanks to its tetrahedral symmetry. However, in the course of the vibrations of the atoms in motion of the molecule, fleeting dipole moments are present as the atoms distort the molecule. In this way, not only the magnitude but also the direction of such a fleeting dipole moment is changing. Methane absorbs richly in the infrared spectrum due to its vibrations. CO2 is a linear molecule. It has no permanent dipole moment, but during the course of its molecular vibrations, it has a fleeting non-zero dipole moment, which allows for light to be absorbed. However, for one specific normal mode of CO2, there is no net dipole moment change because both oxygen atoms are moving back and forth with respect to the carbon atom in phase. By this amount, the so-called symmetric stretching of CO2, this particular vibration of the molecule is not active in absorbing infrared light. The vibrational motions of CO2 are particularly important in carbon dioxide's behavior as a greenhouse gas. Even though CO2 has no permanent dipole moment, it absorbs energy in the form of infrared light due to its vibrational motions. Homonuclear diatomic molecules do not absorb or emit radiation due to vibrational state transitions. By definition, homonuclear diatomic molecules have no dipole moment and no changing dipole as the two atoms vibrate. Other methods are necessary to observe the vibrational energy levels directly.